Physics and forms of heat transfer. So for heat transfer, there are three basic types of heat transfer. The first one is conduction, second one convection, and third one is radiation. And all three are very important for considering in heat transfer. So the first one, conduction, is basically heating by contact. This usually happens between one solid surface and another solid surface. So, for example, heat transfer between your book and the table. There's some sort of heat transfer happening between those surfaces, especially if one of them is a different temperature than the other. Perhaps a more interesting example would be if you put your book on a stove. There would be conduction heat transfer happening between the stovetop and your book. So, that is if you use an electric stove. With this, the type of heat transfer that we have is basically excitement spreading from molecule to molecule. And this is sometimes called diffusion, but basically conduction is very slow. It has to excite one molecule at a time in order to spread heat, in order to spread energy. There's a basic equation that goes with this. So the rate of heat transfer for conduction is given by Q dot, as with most things inside of heat transfer. And it is dependent upon the coefficient of or the conduction coefficient, the surface area of, or the surface or contact area of interest, and the distance the heat has to travel through the object, so how thick it is usually, and the change in temperature, or delta T. So basically this delta T occurs when you have a surface and you want to find the heat at the top or on the bottom, or sometimes somewhere in between, but usually it's the difference between the top of the surface and the bottom of the surface for when you're talking about heat transfer through that surface. So then we have convection. And convection is basically the heating of a surface, or heating between a surface and fluid motion. This can occur in a lot of different places. So like on a solid to gas boundary, or a solid liquid boundary, or a liquid gas boundary. So to kind of describe those, like a solid gas boundary would be like your house, like a wall of your house and the air going across it. A solid liquid boundary would be like a pipe. When you have liquid flowing through a pipe, you have liquid on the inside, solid on the outside. For a liquid gas, that one's a little bit more interesting. That would be where you have a puddle or a pond or a lake or an ocean, and then you have air flowing on top of it. Technically, you have two fluids in contact with each other. However, the important thing in this case is that there is a surface across which convection heat transfer can occur. So, yes, surface is very important. And fluid motion is classified in two different ways, as being turbulent or laminar. Turbulent means that the air is churning a lot. It's forming eddies and currents, and generally, like, the flow may be in a general direction, but once you start breaking down portions of the flow of air, it's very choppy. So if you just take like your standard box fan, and it's just blowing air, once you get about, well, the fan, just for how it pushes air, is going to make all of the air extremely, extremely choppy. So not very even at all. And then with laminar, this means that the fluid flow is very, very straight, and this is actually incredibly hard to achieve inside of large things, particularly with air. Laminar flow, you'll see that a lot in certain cases with water, and you'll see it a whole lot with cases dealing with oil. So, basic convection equation is rate of heat transfer Q dot. And sometimes you'll see a subscript which is like Q dot convection. And then there's your convection coefficient, which is H, given by an H or a minus H, depending on how you define your direction of heat transfer. Your surface area, which is A, and then the difference between the fluid temperature, which is often called T infinity or T INF. So usually they just use the sideways infinity sign. When you see that, that usually means you're talking about some sort of air or fluid temperature. And then you have the surface of the temperature, or the surface temperature, which is usually given by T sub S. Alright, and then for radiation heat transfer, this is basically heat transfer that occurs between two surfaces. And this heat transfer is actually occurring in the form of infrared electromagnetic radiation. So basically a little bit inside the range that you can see like visible light, but for the most part it's all infrared radiation. That's where the heat transfer, that's the EM band, the electromagnetic band in which you find your most heat transfer. And for this, when you talk about really high levels of heat, this is where radiation heat transfer dominates. So let me explain that a little bit. You have your radiation heat transfer, which is your Q dot. Notice how they're all Q dots. You have something called the Stefan-Boltzmann constant, which is 5.67 times 10 to the negative 8th. Your surface area, which is there, and then your surface emissivity. This basically means how well the surface, basically it's how well it can send and receive radiation. It's made up of a couple of components, which are, absorption and reflectivity. And then your temperature of the surroundings, so basically your source of radiation, and then your temperature of the surface. Notice how the surroundings and surface temperatures are raised to the 4th power. So when talking about things that are hundreds or thousands of degrees, these are these numbers get very, very big. Also, because the temperature is to the 4th power, use an absolute scale for radiation always. So this is true of, or can be true of convection heat transfer in some cases, and sometimes in conduction. But in radiation, always make sure to use an absolute temperature scale, which are usually degrees Kelvin or degrees Rankine for the English units. So very interesting piece of or type of radiation, and if you need a good example of this, you can just step outside. The sun or stars or moon will hopefully be shining down upon you, and in there's a small amount of heat transfer for stars and moon, but a rather large one when it comes to the sun.